So now we have this ratio of the receive power to the transmit power. So we know how much power we need to transmit and what the gains of the two antennas need to be in order to receive the amount of power we want over a given distance. But how do we know how much received power do we need? And for that question, the best idea is really to draw a cartoon. So let's say we've got our transmitter over here. Here's our transmit antenna, and it is radiating some waves that are spreading out spherically from it, and some of those happen to go in the direction of our receive antenna. Now our receive antenna accepts those, and that gets transformed into P intercepted, which we talked about last time, and P received once we deal with the efficiency of the antenna. But there are a bunch of other sources of electromagnetic waves in the environment of the receive antenna. There could be car starters. Car starters can make a lot of electromagnetic noise. There could be other radios. There could be noise from the sun and stars and other sorts of sky sources that we call sky noise. There could be thermal noise. Anything with a temperature gives off black body radiation, and some of that is going to land within the frequency band of your signal that you care about. So all of these things contribute to the amount of noise power that is also going to be present at your receive antenna. Now, this is an important thing to note about because I have encountered a lot of interesting misconceptions about noise. A lot of people think that noise is something that somehow gets like picked up and attached to the transmitted signal as it goes along and arrives at the receiver. No, not at all. There can be noise in the transmitter, right? So it could transmit the signal it wants plus some noise from the transmitter. That's fine. But once it's in the air, it's not getting more noise on this signal. What's happening is the receiver is receiving this signal, but the receiver also receives noise and interference from its surroundings. Anything, literally anything can be a noise source, but some things are more prominent noise sources than others. So how do we model the noise that is being accepted by the receive antenna? When we're dealing with noise in a typical circuit, let's say a resistor, the noise power in this resistor is Boltzmann's constant, K, times the temperature of the resistor times the bandwidth of the system that we are using to measure it with. Now, our antenna is not a resistor, but in antenna systems, we can model the antenna as though it is a resistor, in which case the noise power from the antenna is Boltzmann constant times the system noise temperature times the bandwidth. And the system noise temperature is not a real temperature, but it is calculated to be equivalent to all the noise sources that are present in the receive antenna system. Like external sources of noise, and thermal noise generation. In the antenna itself. All of that stuff gets folded up into the system noise temperature. Now, in this class, we're not going to talk about how to calculate the system noise temperature itself. That is for antenna design, so little plug for taking the antenna design elective course, Engineering 435. But if you are given the system noise temperature, now you can figure out what is going to be the noise power at the antenna. What do we do with that information? We figure out the signal to noise ratio. And that is the receive power of your signal divided by the receive power, the noise power at the receiver. A lot of the time we express that in dB, so then we would do 10 log base 10 of that ratio, PRX over PN, and that is what you would get for SNR. A lot of the time people will just write SNR all caps like that. Other times, like in your book, people use the symbol S sub n, but either way, it is the ratio of the receive power to the noise power. So what you do is you set a threshold. I need an SNR of this much. A common number might be that you might need it greater than 20 dB or maybe 10 dB. And then based on that, you use that to figure out, well, if I know my noise power is some amount, then I need my receiver power to be 10 times the noise power if my signal to noise ratio has to be at least 10 dB. And that tells me the answers to important questions like, what is the range of my communications link? Or how big does my receive antenna have to be? Or how much transmit power do I need? All these sorts of things can be answered based on this, because once you know the signal to noise ratio that you need and the noise power that you're going to have, you can figure out how much receive power do you need in your link, and you apply the Friis transmission equation to answer all your questions.